Okay, chemistry time, investigators. Today we are investigating the role of the mole. Oh, let's name it that, actually. That's kind of rhymey. Role of the mole. Role of the mole.
Like
and I, please don't make me restart this video. Let's all focus up. Okay. In fact, I was going to draw a really cute picture of a mole stuffed into like a croissant or something, like a joke about rolls and moles both. A little quadruple entendre for you, but now I'm not going to because I was frustrated. I'm going to do it anyway. He's going to be a happy mole.
I think moles are so cute. I don't hear anyone says I think moles are really cute.
Moles are ugly.
No, they are not.
Okay, stop offering your opinions about whether or not how cute moles are. Does that kind of look like a croissant with like a mole in it, like a pain au chocolat, but with a mole? No, it does.
It looks like a fat Chinese cat.
So the role of the mole, this here, I'm going to put here, this is the role of the mole. I'm going to put the mole in double quotes. There we go. Because we mean both of these words differently. What does the word role mean when it's R-O-L-E?
It means what it's supposed to do.
Okay, I like that. Supposed to do. Supposed to do. Good. And then mole, what do we mean when we say that in science? Please don't actually write the word supposed to do like that, Cyrus.
I did.
Supposed to do. Taylor Homan. Okay, and what do we mean when we say this mole? This is key. This is what you really want to write down. This is actually the first thing you actually want to write down. It's an amount. 6 times 10 to the 23rd. We sometimes call this number Avogadro's number. After Amadeo Avogadro, a Portuguese or Italian physicist?
I think it's Italian.
I think it is Italian. An Italian chemist and physicist from the 1600s, I believe. A lawyer and physicist. I'm sorry. And he was the first to reckon that we can, using this number, we can fairly easily convert from, and this is the point of this, convert from use, the role, as it were, is to convert from mass, usually in grams, to amount of atoms. Is this a very large number or a very small number?
Very large.
It's very large. It's 6, we could write. It's 602 and then 23 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. That was a lot of zeros. I think I did that right. Someone in their lab calculated that if you had a mole of, what did you use? Sugar babies? What was it? Sour Patch Kids. If you had a mole of Sour Patch Kids, about that size, right, ish, how many light years would that be? Conveniently, I have your lab right here. It would be, she says, if you had that many sugar babies, that's not its name, Sour Patch Kids, it would be, this math seems wrong. So we'll just ignore that for a second. Would you please hand those out to the people? But it's huge. Just that many of the little sugar babies would be many, many, many thousands of miles, for instance, because it's such a big number. The common way we kind of relate this to your modern understanding is that this is a number that is itself a unit, kind of like dozen. You can have a dozen of anything, really. Could you have a dozen sophomores?
Yeah.
I mean, you couldn't have, probably, but you know what I mean. Could there be, for instance, a dozen sophomores in a room?
Yeah.
Yeah, of course. Dozen applies to sophomores. Could you have a dozen eggs?
Yeah.
That's a very common thing to have. Could you have a dozen Pepsis?
Yeah.
Yeah, 12 Pepsis is a very common thing to have. Could you have a dozen atoms of calcium? Yeah. Let's all focus up. Could you have a dozen? Could you have 12 atoms of calcium. Could you have 12 atoms of calcium?
Yes.
Yeah, you could. There could exist 12 atoms of calcium, but would that show up? Would that have any kind of macroscopic meaning at all? No. The point is that many calcium atoms, or any other atom, or any molecule, would be way too small of a thing for us to work with. And so we work in terms of this number. In the same way that, for instance, egg merchant, just one of the usual jobs you can sign up for after high school. If you are an egg merchant, you deal in dozens of eggs. When I think Mr. Sintley's dad, when he worked at there was an egg factory. That sounds wrong. I think I'm saying the wrong things, but they would have worked in dozens or dozens of dozens gross of eggs, because that's a usual thing. And it's the same way when we deal in atoms, we deal with moles. So it allows us to convert from mass to amount of atoms. And that number is the relationship between those. The song, do you remember the song? Says something like, if there were a mole of pennies, everyone on the world would get $1 trillion, right? A mole of pennies divided by how many human beings there are, man, woman, and child in the world, would get something like $1 trillion worth of money. It would ruin the economy. Not least of all the copper economy, but that's a lot of money. And the point is that this number is huge. But a mole of atoms, a mole of maybe sodium atoms, or a mole of sodium chloride ions would fit, the song says, in the palm of your hand, because atoms are so small. So we use this to convert from mass to amount of atoms. That's the end of that little spiel. And the way that we do that usually is by using Avogadro's number and the molar mass. So the two quantities that we need for this are Avogadro's number. Tell me what that is.
6.02.
Thank you, 6.02 times 10 to the 23rd. And molar mass for a given atom, or I'm going to put compound, but that could be either molecule or formula units. Where do we find this? Where do we find Avogadro's number? It's in our where? Memory. Memorize. You need to memorize this number. Where do you find this? Where do you find the molar mass for an atom or a compound? What is your main tool for that? The periodic table. Molar mass for a given atom or compound, and we need Avogadro's number. So let's do our sodium one. Let's say we have 1 mole of sodium atoms. One mole of sodium. It's a conversion, so what would my next step be?
Multiply by...
Yeah, conversion bar. What do I want to eliminate? What do I want to get rid of? What do I want in this case, denominator? What's the unit? What's the unit?
Of mole.
Moles of what?
Sodium.
Sodium. And if I want to find out how many atoms that is, I would then convert to atoms of sodium. And then I ask myself, in 1 mole of sodium, how many atoms of sodium are there?
We don't know.
We do know. And let's think about it this way. Let me start with a little bit easier problem. Let's keep this one up here, but I'm going to do another one in red. Let's say we have 1 dozen roses. It's Valentine's Day, so this will work great. 1 dozen roses. We want to get rid of.
What?
What's
We want to get rid of.
dozen what? Roses, and we want to go to number of roses, or individual roses. I ask myself, in 1 dozen roses, how many roses are there? Exactly right, 12. So how many roses do I have if I have 1 dozen roses? 12 roses. Now let's do it this way. Let's go back over here. In 1 mole of sodium, how many atoms are there of sodium? You got it. 6.02 times 10 to the 23rd. So in this case, in my 1 mole of sodium, how many atoms of sodium do I have? Again, 6.02 times 10 to the 23rd atoms. Very simple in both cases. Do you see how these two things are related? What is the method by which we do this? So we have these two things are our materials. What are the tools we use to work with these materials? What's the one tool we use to work with them?
Let me think.
All right, mine.
Yeah, conversion is also called dimensional analysis. I'm going to put dimensional analysis. So our old friend unit conversions. risen not from the grave, but maybe from the depths of the river Styx. The depths of September. Wake me up when September ends. You remember that one. The reason we were singing Wake Me Up When September Ends is because you guys hated conversion so much. And now they are back, revivified into the form of molar mass conversions. Let me have some more Celsius. Other brands are available. Let's talk about that again after class. Let's do it. Let's make this a little bit more complicated. Let's say now, instead of 1 mole of sodium, let's say we have 2 moles of gold atoms. I would love to have 2 moles of gold atoms. Let's find out. How many atoms of gold do I have then? I have more than 2 atoms of gold. No. Tell me what to do. I'm not asking you the actual answer. Tell me what to do. I want you to do this in the same way that I'm doing, as I told you at the beginning of the year. I want you to do the get rid of step first. I want you to do the units first. So get rid of moles of gold. What am I going to? What unit am I going to? Atoms of gold. Now I ask myself, in 1 mole of gold, how many atoms are there of gold?
6.02.
And where did you find that number on the periodic table? Memorize. Okay, now with my calculator, stand by while I get the calculator. I'm going to be using for this a TI-83. Other brands are available. I'm going to type in 2 times, I'm going to type in 6.02 second E. You guys have calculators like this? 23. So it ends up looking like this. The capital letter E. Don't use lowercase e. That's Euler's number. That will not work for this. The capital letter E on these kind of calculators means times 10 to the. And that ends up being, my answer is 1.204 times 10 to the 24th atoms of gold. Now we're going to hold on to this number. I'm going to just use my Dremel tool to saw this out of the board and hold on to it. Okay, I'm going to hold on to that number because we're going to do another math with it pretty soon. But do you see kind of how to use your calculator for these?
Yeah.
Why would I need to use my calculator for this?
Because we can't do it.
No, I don't say you can't, but the number is big and it has a scientific notation in it. And so I would encourage you to get good at scientific notation by doing these ones, because you're going to have to eventually anyway. And I really think this tool of the little baby e, which is again second comma, is going to be super useful to you, because that takes the place of the whole thing. Let's make a little side note box here about calculators. Let's label it TI-83. This whole thing that you would write times 10 to the something on your calculator is just this letter E, something. It actually is double E on the key here too, but when it shows up on the screen, it's just E. I don't know. I don't know what it stands for. Exponential exponent. On va voir. Okay. Hold on to this number.
You say what?
Could we do this the other way around? What if I'm going to erase this top one. Is it okay if I erase this top one?
Yeah.
Let's do it like this. Let's say I have 568 roses.
Your wife's going to love you.
I got them from her. So 568 roses. And I'm going to figure out how many dozens of roses that is. Okay? Conversion bar. Right, now in this case we're doing roses, which I spelled with a Z this time on accident and to be cool. And I'm going to convert that to dozen roses. I ask myself again, how many roses are in 1 dozen?
407.
Taylor correctly points out, why don't we just divide 568 by 12? For this one you can, right? The same question, why don't we just multiply 2 times? Well, this is where it becomes difficult. Let me reiterate a point that I make several times to several different people, and some of them choose to learn and some of them choose not to. If you do it like this, when it's easy, you will know how to do a good job when it's hard. If you always take the easy way out and just divide 568 by 12 and write down your answer, you won't know how to do it when it's hard. What is it?
47 point repeating.
So it'd be 47.
47.3 what?
Repeating.
No.
Dozen
roses.
Which is technically
In the same way, we can do it with, let's say we have 1.7 0.39 times 10 to the 24th atoms of silver. We like silver. I have my conversion bar already. What should I do next? I'm sorry, we're going to moles. So we're going to go from atoms of silver, right, to what?
Moles.
Moles of silver.
So you put atoms of silver as your denominator.
Yep, atoms of silver is the denominator, moles of silver is the numerator. What numbers do I put on these lines? Self, you say to yourself. Self?
So you would put how many atoms are in one mole?
And how many moles, Gabe?
One.
1 mole. That's how you remember it. In 1 mole, there are 6.02 again times 10 to the 23rd. With my calculator, I type in 1.39 E24 divided by 6.02 E23. I end up with 2.31 moles of silver. How did I get moles of silver? Well, my atoms of silver crossed out. One thing you might notice about the way that I've been doing these problems, and I would like for you to do them the same way, is that I'm always putting not only the unit, but the thing that the unit is applying to. So not just moles, but moles of gold. Not just moles, but moles of silver. Please don't do that, Taylor. Not just dozen, but dozen roses.
Perfect. I like your bonbon.
You like that what?
Yeah, bonbon.
You can go to the office.
Why?
Okay, be quiet and take notes. Okay, the other thing we can do with these, the whole point of this is to convert from mass to amount of atoms, and spelled the word and wrong, and vice versa. The other thing we do with these is we can use them for mass. So we might say something like, if I have, for instance, 1.204 times 10 to the 24th atoms of gold, I can convert that to a mass of gold. How would I do that? What should I do first? Where this number came from? Remember, this was the one I kept from earlier. I was going to Dremel tool it out. Okay, so first I'm going to do my conversion bar. How am I'm going to trying to get from atoms to mass. What's the intermediary between those? Do you guess? Moles. Good. So I need to first go from atoms, right, to moles. Not just atoms and not just moles, but atoms of gold to moles of gold. And then I'm sticking with my units. I'm going to go from moles of gold to grams of gold. Talk about that in a second. First, let's fill in these numbers. In 1 mole, in 1 mole of gold, I have 6.02 times 10 to the 23rd atoms of gold. Where do I get these numbers from? Can you guess where on the periodic table I might find how many grams are in 1 mole of gold? Probably not in memory. What number up here might tell me how many grams are in 1 mole of gold?
The number
79.
It's not 79.
19.3.
The mass number.
It's not 19.3. The atomic number, that's it. This number is defined as, remember we found it earlier in chapter 4, I believe, we can use the number of protons plus neutrons to give us an isotope. The weighted average of those isotopes, like in your Snackium lab, gives us this number. But this also happens to be, I'm putting this in quotes on camera, happens to be, because it doesn't actually happen to be, the number of moles in 1 gram of that. That was the relationship. This number is the relationship that Amadeo Avogadro made to this number. This many of some atom has a mass that is the same as the average atomic mass of its isotopes. That relationship was his discovery. And so we use that number, 196, read it off to me because I don't have it memorized, 196 point what? 967 grams. Do you see where that number came from? Where did that number came from? It's the atomic number. And it's not just a coincidence or a miracle, although it might be those two things, that number is the same. It's because that's what his discovery was. That's what Avogadro's number is. That's why he didn't just say, let's have it be 12 atoms. That's why this number is kind of janky, is because this number of atoms being that mass is what he discovered. Okay, so now we on our calculator type, we start with our given. I hope you have your calculators out. 1.204 E24 divided by 6.02 E23 times 196.967. I get 393.967 0.93 grams. 393 grams is probably, I would guess, about the mass of my, maybe it's a little bit more, maybe the mass of my teacup and calculator together. This is probably about 400 grams. Would I be happy if I had this much gold? I would probably be a little bit happier if I had this much gold than if I had this much calculator and teacup, but I would have to buy a new calculator. But that's kind of a lot of gold. So this 2 moles of gold is kind of a lot of gold. Math good. Math good?
Math good.
Okay.
Amazing. So for every element that you're trying to get into grams, you always use the atomic number?
Yes, let's get to the next step.
Slay.
Slay. Let's say instead of gold, I'm going to erase this bit. I hope anyone's writing this down, although it seems like you're not. It'd be insane for you not to write this one. I'm just basically telling you exactly how to do it. Let's say that instead of that mass of gold, I have that mass of water. 393.93 grams of H2O. Now, I hope you notice where the problem is.
H2O.
The problem's right here. No, what's the problem?
H2O.
Okay, H2O is the problem. Why?
Because it's two different elements.
Because it's a compound,
Yeah.
not an atom. So we're going to do it the same way, though. So we're going to go from grams of H2O to what? We're trying to find how much. Sorry, I forgot to tell you the actual problem. The problem is we want to try to find how many molecules of water that is. Okay, so I'm going to go from grams of H2O to what?
Moles.
I can't go from grams to molecules, can I? I have to go first to moles. Grams of water to moles of water, and then from moles of water to molecules of water. Do you see why I'm using molecules now instead of atoms? Do you? Is water an atom? No. What are atoms? No. The opposite of that. Individual atoms are what? They're the simplest particle that makes up an element. So if it's just an element, we call that representative particle an atom. Let's start our representative particles box over here. Representative particles. I hope you're going to write this down at least.
But an atom molecule formula is unit.
So, yep, exactly. The representative particles. If it's an element, the representative particle is an atom. That is, an atom is the most basic bit, the most basic chunk of that element. If it's a covalent compound, it's a molecule. The molecule is the most basic chunk of that covalently bonded compound. Hey, how can I tell if a compound is covalent or ionic? It just screams it at me all throughout the universe? Wrong.
Oh, it's because a covalent bond is between a metal and a non-metal.
You're on the right track, but you're wrong.
Oh, because they're bonded via their covalent.
They're both, they do share electrons. How can I tell? They're both nonmetals. If both substances or both or more atoms in it are nonmetals, we probably think it's covalent. Anyway, and then if it's ionic, was that wrong, Lily? Did I say something wrong? Was that you screaming? Okay. Ionic compound we call a formula unit, usually abbreviated just to FU. And then if it's, there was another one, right? What was the other one? That might be all.
Molecule?
No, we already got a molecule up there. But those are the different representative particles. Oh, it could be, if it is just itself an ion, we call that an ion. Like if you just have a mole of sodium ions, for instance. Okay, anyway, so how many, this is the part that's kind of a sticker for us here. This little bit to get this, what we have to do, can you guess? I hope you can guess. How could we find the molar mass? Remember, that's grams per mole for water. It's not going to be up here, or at least it's not. Where's water up here? Exactly right, Kesslin. Add them. So what we do, I want you to write them always this way. And so I hope you write this down, because when I say I want you to write them always this way, instead of looking at text on your watch, I hope what you're doing is writing down the way I want you to do them. H and O. Why would I pick H and O? That's not it. I'll probably have to cut that. But why? Yeah, it's because those are the elements that are in water. And then we write down their molar masses. What's the molar mass of hydrogen, and how do I know?
Hydrogen is 1.008,
and it's because that's what's on the periodic table. At some point this was discovered, but for us it's because it's on the periodic table. Oxygen is 15.999 grams per mole. Do you notice I'm including numbers with these units? Whoops. Do you notice I'm including units with these numbers? Yeah, heck yeah I am. And then, is this going to give us the right answer? Why?
No way.
there's 2 hydrogens. So I need to multiply that by 2, end up with H2O equals 1.008 times 2 is 2.016 plus 15.999 is going to give me right about 18-ish, 18 point, no, 18.015, I think, grams per mole. Yeah, you can. Yeah, I want you to do this on the calculator usually, but I just did it in my head. So this number is how many. Look, hey, check this out. This is the same. You don't have to write this every time, but this is the same as 18.015 grams over 1 mole, and that goes straight up into there. So in 1 mole of water, there are 18.015 grams of water. How many molecules of water in a mole of water? How many? Did I say it right? I might have just...
Yeah, how many molecules are in 1 mole of water?
Let's not do that anymore, okay? Instead of doing that, let's take notes.
I am.
Okay, well, I said instead of, not in addition to. Okay, how many molecules are in 1 mole of anything? 6.02 times 10 to the 23rd. Okay, so then in my calculator, I write 393.93 divided by 18.015, enter, times 6.02 E23. And I end up with 1.31 times 10 to the 25th molecules of water. 25th. That's 25th. Why is this not the same as my, look, these two numbers are different. Why?
It's a different outcome.
It's a different,
It got bigger.
what has different masses?
H2O and gold.
Yeah, water and gold have different molar masses, and therefore these two numbers are different. They have the same mass, remember? I started out with the same mass, or in this one I ended up with the same mass, but they have different number of particles because gold has a larger molar mass, and therefore it would take fewer moles of gold to make this many grams of gold. So let's recap real quick. The things that you need to know at this point are how to add up to find the molar mass of compounds, and then how to use conversions to convert between mass, moles, and atoms, or mass, moles, and representative particles. The mole is a unit, right? Or have you heard? Containing 6 times 10 to the 23rd. That's 6 with 23 zeros at the end. That's much too big a number to comprehend, but we're going to use it all the time. The last thing we're going to do today is called empirical and molecular formulas, and this gets a little bit complicated, so I'm really hoping that you have the ambition and ability to practice these on your chapter review and worksheet, because sometimes people don't have a very easy time with these. This stuff should be pretty easy. What basic tool are we using for these? Conversions. These are basically unit conversions. The numbers are kind of big and wonky, but this shouldn't be too hard. There's another step that's added. Really, fundamentally, this is the thing you learned that's new today. If you already knew your vocab and you already knew how to do unit conversions, both of which I'm a little bit sketchy about, this should be the one new thing you've learned today. Now let's learn a new thing that actually kind of combines all of it. I'm going to erase this mid part here. I am going to leave my roll mole, though. Roll of the mole. That was cute. It wasn't as cute as my intro last year, but it was still pretty cute. And now we're going to do empirical and molecular formulas. Empirical and molecular. I will start a new page for this. Formulas. What's a formula?
What's a what?
What's a formula?
Formula? Something
A
like
squared plus
right
B
here.
squared equals C squared. There was
In chemistry, what's a formula?
delta equals H over V.
A formula is. I don't know the exact definition.
What's a chemical formula?
A chemical formula is the equation that we use to.
Solve a problem.
Let's spit it out, dude.
It's the equation
What?
we use.
I'm amazed at this. This is a chemical formula. It's just the tells us the ratio of the elements in a compound. So I wish you'd write that down. A formula tells us the ratio of the elements in a compound. This is empirical and molecular formulas. So what we do with this, we'll usually start out as we would get a reading from a mass spectrometer of percent mass. The example your book gives is percent mass of C is 48.64% C, 8.16% H. I might switch colors after I write these, and 43.20% O. This is a readout. So this would be the given. This is what we might be given in a problem where we do these. And we are to find the empirical and molecular formula. So given this information that I hope you're writing down, we are to find the empirical formula. The first thing we need to do, step 1, is convert each mass to moles. The implied step here is that we pretend these percentages are masses. I hope this becomes apparent to you, but basically we assume that we have 100 grams of the substance and we use all these percentages as if they were just masses. So we convert each of these to moles. 48.64 grams, 8.16 grams, and 43.20% grams of C, H, and O respectively. So that's step 1. Well, it's half of step 1. Now, using the information that we learned earlier, we convert each of these to what? I just told you, moles. Moles. In each of these, 1 mole is, where can I find the mass of 1 mole of each of these? No.
Here.
The periodic table, yeah. What is the mass of 1 mole of carbon?
Let's look.
Let's look. No.
12.013 or 011.
12.011. What about for hydrogen?
1.008.
Okay. What about for oxygen?
15.999.
Okay. Each of those we calculate with what? Our handy dandy calculator. Type them in. So I type in 48.64 divided by 12.011. I get 4.04 moles of C. I type in 8.16 divided by 1.008. I get 8.09 moles of H. And I type in 43.20 and divide that by 15.999. I get 2.70 moles of oxygen. Step 2 is divide each mole by the smallest. Effectively, what am I going to get if I divide them all by the smallest? A what? That starts with R in math. A ratio, exactly. Hey, have we heard the ratio word one other time in this lecture before?
Yeah.
Yeah,
That's the ratio.
it's the formula. This is a ratio. So by doing this, I'm going to divide each of these by the smallest. What is the smallest? Oxygen. So 2.70, 2.70, 2.70. What's 2.70 divided by 2.70?
Here.
Are you kidding me? What's 2.70 divided by 2.70? 1. Good. What's 8.09 divided by 2.70? I get 2.99. And what's 4.04 divided by 2.70? I get 1.49. I'm running out of room to write my steps, so I'm going to put 3 on top of 1. But step 3 is multiply each by a whole number to get a whole number ratio. The trouble here is that one of these is 1.5. Do you see that? It's 1.49, but it's basically 1.5. What can I multiply all of these by so that I get whole numbers only?
1.
That won't work.
2.
Okay, if I multiply all of them by 2, will I get whole numbers only? Well, let's try it. What's 1.5 times 2?
3.5.
Maybe you just stop talking for a second. What if we multiply them all by 2? Okay, what's 2.99, which is 3 times 2? 6. What if we multiply this one by 2? What's 1 times 2? 2. This is the ratio. These are all whole numbers, right? So that's our ratio. It's C3H6O2. Do you see where those came from?
Yeah.
It was the C is 3, the H is 6, and the O is 2. And those give us this empirical formula. This is called the empirical formula. Empirical means we found it with our own eyes, or the evidence showed us, and that's because the evidence might be these percentages. That's the empirical formula. I'm going to make a note just real quick because we're out of time, but I'm just going to say that if you're trying to find the molecular formula instead, we'll do practice with this in real life, but just for the sake of the video, if you're trying to find the molecular formula instead, what you do is you add the molar mass of all this up and divide that into the given molar mass, which will give you another whole number, which if you need to, you can multiply all this by. That's it in a nutshell.